Bismillahirrahmanirrahim. Once again, I would like to start a new method which is known as Cauchy-Euler homogeneous differential equation. Why it is known as homogeneous differential equation? Because we have the similar degree of polynomial with the similar order of differential. So here, look at this. We have a polynomial of degree n with the order of differential n. Similarly, the second term would be x minus 1. This is the uh, degree of the polynomial, and this is the order of the polynomial. And look at this. If degree and order of the polynomial are same, this kind of equations are known as Cauchy-Euler differential equation. So here we will use a specific technique to find the solution of the such a kind of differential equation. In this type of differential equation, we will apply some substitution for obtaining the solution. What are the substitution? Our substitution are, we will always consider x is equal to exponential t, and x into capital D becomes delta, and x square d square becomes delta into delta minus 1, and x cube d cube becomes delta into delta minus 1, delta minus 2, and so on. And here delta is what? Delta is the differential in for the differential with respect to t, that is d upon dt. So now we will solve a problem and see how we can obtain the solution by using the Cauchy Euler differential equation by using this method, which is known as Cauchy Euler to obtain the solution of Cauchy Euler differential equation. Here we have a problem: x square d2y upon dx square minus 2x dy upon dx minus 4y is equal to x raised to the power 4. In this problem, we can easily observe that we have the second degree polynomial with second order differential and first degree polynomial with first order differential. So here, how to pursue the solution? First of all, we will write this polynomial, this differential equation in term of the capital D. So for instance, d2 upon dx square, we will write d square minus 2x d upon dx becomes capital D minus 4, and taking common y from the entire terms is equal to x raised to the power 4. In this equation, we will apply the substitution. What are the substitution? We will assume x is equal to exponential t, and delta x is x multiplied d is equal to delta. For instance, x square d square, substitute delta into delta minus 1. So in equation number 1, we will obtain, for instance, x square d square, we will substitute delta into delta minus 1 minus 2 delta, that is 2 xt, that is 2 delta minus 4 y is equal to exponential 40, because we are substituting x is equal to exponential t. So when we will substitute exponential 40 instead of x, exponential t raised to the power 4, power will be multiplied, so that we can write it as exponential 40. Now further simplification: delta square minus delta minus 2 delta minus 4 into y times is equal to exponential 4x, delta square minus 3 delta minus 4 into y is equal to 4. This is the differential Cauchy-Euler differential equation has been transformed into the delta. For pursuing the solution, we will consider the left hand side to find the complementary function from the differential equation. So how to find the complementary function for the differential equation? By taking the auxiliary equation, that is auxiliary equation from this equation, m square minus 3m minus 4, that is m square minus 3m minus 4 is equal to 0. By factorization, we will obtain two factor, m is equal to 4 and m is equal to minus 1. The complementary function for the differential equation will be yc is equal to c1 exponential 4t plus c2 exponential t, because this differential equation is in term of the t. Therefore, we will not use write here x. For instance, we will use t here. Now we are going to find the particular integral from the above equation, that is equation number 2. Y is equal to particular integral, that is 40 upon delta square minus 3 delta minus 4. Same method we will apply here, as we will substitute what? The power of uh, coefficient of power of the exponent we will substitute here. If after the substitution, that is f of b, f of d will be transformed into f of b such that f of b not equal to 0. So this theorem, because a exponential bx f of d is equal to a times exponential bx upon f of b when f of b not equal to 0. So after the application, we can see that yp is equal to exponential 40, 4 square minus 3 into 4 minus 4, that is 16 minus 16. It means that this is not equal to 0, rule is failed. So in that case, what happened? In that case, we will multiply the entire term by t and differentiate the denominator. So the differential of the denominator is t square minus 3t minus 4. So the differential of t square with respect to t, or d square with respect to d, delta square will be 2 delta and minus 3. So this is 2 delta minus 3. For instance, delta will substitute the value of b, that is 4. So 2 times 4 minus 3, that is 5. So this is our yp. Now the general solution can be written as y is equal to c1 exponential 4t plus c2 exponential minus t is equal to t upon 5 exponential 4t. Now we will apply again the substitution. We know that x is equal to exponential t, so that x raised to the power 4 will be equal to e raised to the power 4t, and ln x is equal to ln x will be t. So x raised to the power 4 is equal to exponential 4t, because x is equal to exponential t, and ln t is equal to t time of ln exponential, and we know that ln exponential, the value of ln exponential is 1, therefore ln x will be t. We will substitute all the values in the above equation. This is the general solution. So now the general solution becomes y is equal to c1 x raised to the power 4 plus c2 upon x plus ln x upon 5 into x raised to the power 4. Because our question was in x and y form, so that when we will finish our problem, we must be transformed from the arbitrary function to the real function, that is x and y. So now look at this, another problem we are going to solve by using the similar method. First of all, we will check is it equation is the Cauchy-Euler equation or not. Look at this here. We have x square, that is second order polynomial, but differential order is 3. And here polynomial order is 1, order differential is 2. So that here we must need third order polynomial to apply the method of Cauchy-Euler method. So according to Cauchy-Euler method, we must be multiply the entire term by x. So after multiplication by the x to the entire term will be transformed into the Cauchy-Euler equation, so that when we will multiply by x, this x square will be x cube, and this one can be written as d3 plus 3 times x into x will be x square, and this will be the x d square plus, and here we have only y, that will be the xt, that is d upon dx, that will be d, and into x d, and y is common, and this x square will be x cube into ln x. Now our equation has been transformed into the Cauchy Euler equation. According to the rule, we'll substitute here according to the appropriate substitution. Here we will substitute x is equal to exponential t, so that ln x is equal to ln exponential t, that is ln x is equal to t only. So ln x is equal to t for x into d becomes delta x square d square will be x in delta into delta minus 1, and x cube delta cube will be delta x cube d cube will be delta into delta minus 1 into delta minus 2. So substitute all the values in equation number 1. Equation number 1 becomes delta minus 1 delta minus 2 plus 3 times delta into delta minus 1 plus delta into y is equal to exponential 3t into t. Now after multiplication, we obtain delta cube minus 3 delta square plus 2 delta minus plus 3 delta square minus 3 delta plus delta into y times is equal to exponential 3t into t. Few terms will be cancelled out, only delta cube will be remaining term here. So delta cube y is equal to exponential 3t into t. Now what we have to do further? First we will find the complementary function for the differential equation, and you know that complementary function can be obtained from the homogeneous part. That is, we can write the auxiliary equation, that is m cube is equal to 0. All three roots are 0. So the auxiliary, so the general, so the complementary function can be written as y is equal to c1 plus c2 x is t, plus c3 x square. So for instance, x square, we will write t square into x e raised to the power ax. A is 0, so 0 t. So the yc becomes c1 plus c2 t plus c3 t square. Now we are going to find the particular integral according to the from equation number 1. Yp is equal to what? Exponential 3t into t t times whole divided by delta q. And here, what is the value of b? 3. So directly we can apply this formula. A exponential bx upon f of d g of x can be written as a times exponential bx whole divided by f of d plus b into g of x. According to this formula, exponential 3d will write in the beginning, and this factor will be 1 upon delta plus 3 whole cube into t, and apply, shift this term into the numerator, so power will be negative. Now we'll break the taking common 3 from this term, so that this will be what, when we take the common 3 from here, 3 we will write here in the denominator, because 3 is not present with this, with the delta. Now break the power onto the both terms, so this 3 raised to the power minus 3 would be 1 upon 27, and here we miss the 3 in the denominator. So do correct the problem here. 3 is missing. So whenever mistakes are coming in the problem, I will try to recognize the mistake, so you can do it yourself. So here 3 is missing. So according to this formula, 1 plus x raised to the power minus n is equal to 1 minus nx plus n into n plus 1 x square upon 2 factorial minus n plus 1 n plus 2 x cube divided 3 factorial, and so on. So according to this formula, we will use the alternative sign. So this will be exponential 3t 1 upon 27, and this bracket apply the same binomial formula, 1 minus 3 delta plus 6 delta square minus 10 delta cube into t. Because we have linear polynomial, so these two terms will be neglected. Only we will consider here 1 minus 3 delta. Only we will take two terms, that is 1 minus 3 delta into t, and due to the linear power of t, this delta cube and delta square will be neglected, and we know that delta is the differential in term of t, so that derivative of t with respect to t will be 0, will be 1. 3 into 1 would be 1. So solution of this differential equation will be here exponential 3t upon 27 t minus d upon dt of t, that is 1. So in the end, we know that t is equal to ln x, then x is equal to exponential t. So we will substitute the values. Yp is equal to c1. This is the general solution. Yp is equal to c c1. That is y, not yp. This is y. Y is equal to c1 plus c2t plus c3 square t square plus exponential 3t into t minus 1 divided by 27. So y is equal to this. So this is the answer of this differential equation. Now we will see another method. This method is known as Legender's homogeneous differential equation. In the Legender's homogeneous differential equation, how to recognize such a kind of differential equation? Look at this. Here we also have a polynomial with the similar degree, with the similar differential order. So when we have a polynomial of n order, we must have the order of similar order of differential with that. Similarly, the next term is this. Look at this. The next term is also a plus bx whole power n minus 1, and we also have similar order of differential with that. So this kind of differential equation, when we have a polynomial, this what is the difference between these uh, genders and genders and Cauchy's differential equation? In Cauchy's differential equation, we have only uh, coefficient x in the coefficient of the differential, but here we have a polynomial in the coefficient of the differential. So here, look at this. Everywhere, similar polynomials are in the coefficient of the differential. Here a plus bx and also a plus bx, and in the rest of all terms we will have the a plus bx. So that this kind of differential equation are known as Legender's homogeneous differential equation. And here we will apply the substitution to pursue the solution of such a kind of equation. And what are the substitution we will use here? For instance, a plus bx, we will substitute exponential t, and t becomes ln a plus bx. And for instance, delta would be d upon dt, and a plus bx times d upon dx will be b delta. Similarly, a plus bx square d square would be b square times of delta into delta minus 1. Similarly, a plus b x whole cube d cube is equal to b cube delta into delta minus 1. So it's, before this, we we didn't have the b into b square into b cube. We have the delta into delta minus 1, delta into delta minus 1, delta minus 1. But now, due to this factor which is present into the coefficient of d, we must be use b with the delta, that is b square and b cube. It is increasing with respect to the term uh, involving a higher power. So look at the problem, how we can solve such a kind of problem associated with the Legender's differential equation. So first of all, we will see this differential equation and check is it the Legender differential equation or not. So the given differential equation is 1 plus x whole square d2y upon dx square plus 1 plus x power 1 into dy upon dx, and into y, we can write it as 1 plus x power 0. So here, so look at this. This equation is similar as Legender's homogeneous differential equation, so that we can write it as 1 plus x whole square into d square, 1 plus x into d plus 1, and taking over y from the entire term, and the right hand side would be sine 2. For instance, x will substitute, for instance, sine 2 ln 1 plus x will can be written as what? Sine 2 ln 1 plus x, it will remain as it is. So for instance, ln, because we will consider here 1 plus x is equal to exponential t. So uh, log of 1 plus 1 plus x would be only t. And for instance, delta will substitute 1 plus x into d. For instance, delta into delta minus 1, we will substitute 1 plus x square into d square. Why not b is here? Because the value of b is the coefficient of x. So the coefficient of x is 1, we will substitute 1 here. 1 will multiply by delta, that would be 1 into delta, that is delta. Similarly, 1 square will be the 1 square into delta minus 1, that will be delta into delta minus 1. So after substituting in equation number 1, we obtain delta into delta minus 1 plus delta plus 1 into y times is equal to sine 2t, because the whole entire angle is only will be equal to t. So that this will be right as delta square minus delta plus 1 into y is equal to sine 2t. This delta will be cancelled out. Delta square plus 1 into y is equal to sine 2t. This is our equation number 2. Now we will find the solution of this differential equation by the ordinary method. So first we will find the complementary function by taking the auxiliary equation from this equation, delta square plus 1. Directly auxiliary equation becomes m square plus 1 is equal to 0. So from this, m square is equal to minus 1, and m is equal to 0 plus minus iota. This is our complex number. So the complementary solution becomes yc is equal to c1 cos x plus c2 sin x exponential ax. A is 0 here. So yc is equal to c1 cos t plus c2 sin t, because delta is a function of t. Now, particular solution of the differential equation from equation number 2, yt is um, yp is equal to sin 2t upon delta square plus 1, and we will use here this formula because sin bx upon f of d square can be written as sin bx upon f of minus b square. So what is the value of b here? B is 2. So for instance, d we will substitute minus 2 square plus 1, that is minus 4 plus 1, it is minus 3, that is minus. So minus sin 2t upon 3, this will be the particular solution, and the general solution of the differential equation will be y is equal to c1 cos t plus c2 sin t minus sin 2t upon 3, and here we will apply the backward substitution because we know that t is equal to what? Ln 1 plus x. For instance, all the t's will substitute ln 1 plus x. So the general solution will be now y is equal to c1 cos ln 1 plus x plus c2 sin ln 1 plus x minus 1 upon 3 sin 2 ln of 1 plus x. So this is our required solution for this differential equation.